Good morning one and all. In today's lecture, we will start the unit number 3. Okay, before going on that, we have completed the second unit, shear force and bending moment diagram. Right? Something from the unit number 2 will require to solve the bending stresses as well as the shear stresses numerical. Okay, you know how to draw the bending moment diagram. Okay, we have already learned in the unit number 2. Okay, we will go to the unit number 3. What is the unit number 3? You have given the bending stresses and shear stresses of a beam. Okay, here we will consider the different sections. Okay, I section is there, C section is there, rectangle section is there, circular section is there, etc. Okay, you will given the different section. With the help of that different section, you have to calculate the bending stresses as well as the shear stresses on the given beam. Okay, clear? Then how to calculate that? We will see the one by one. Before going on the numerical, you know the some formulas. That's why I will here explain the theory bit. Okay, before going on the numerical. First is what is meant by bending stress. Bending stress, it is also known as a flexural stress. Flexural stress. Whenever, remember that a beam is subjected to the external transverse loading. Okay, external transverse loading. Then this beam will be bent. Otherwise, that beam will not bend. Remember that. If there is a external loading, we will take the example of the simply supported beam. Okay, simply supported beam. Okay. If you acting some external load on that beam, suppose here is a point load, then this beam will be bent from its original position. Otherwise, this beam will be not bent. Okay, we are not consider here self weight. Okay, remember that we will consider the some assumptions. Okay, we will go through the details, but remember that if there is a external transverse loading is there, then this beam will be bent in this way. Okay, then what is meant by bending stresses? What is meant by bending stresses? The stresses is induced in the given beam. Okay, suppose this is a simply supported beam. The stresses, when you apply the external load on the beam, then the stresses is induced in the given beam to resist the bending moment. To resist the bending moment is known as a bending stresses or flexural stresses. Okay, all of you getting the definition? The stresses induced in the beam to resist the bending moment is called as a bending stresses. It is denoted by sigma or F. It is denoted by the sigma or F. Some books you will get the notation sigma, or some books you will get the notation F. Here we are using the notation sigma. Okay, then we can write sigma is equal to m by j. Again, what is meant by m? What is meant by m? Is the moment of resistance. Moment of resistance. Moment of resistance. Remember the meaning of this. M is the moment of resistance. You know the how to calculate the bending moment. We have learned in the second unit. Okay, moment is nothing but the force into distance. Force into distance. You can calculate any point moment. At point A, at point B, at point C. You can calculate, and you know how to calculate that moment of resistance as well as moment. And what is the Z? What is the Z? Z is denoted by sectional modulus. sectional modulus. Okay, remember that. Again, what is mean by sectional modulus? Again, what is mean by sectional modulus? Z is equal to, we can write the standard formula I by y. I by y, or we can say the I by x is there. I by x is there. Okay, what is the I? I again is moment of inertia. Moment of inertia. Okay, you have learned in the physics what is the moment of inertia. If we have given the rectangular section, then we can write the BD cube divided by 12. Okay. In circular section, again you will get the different formula. If you are getting the triangular section, again this moment of inertia will be changed. It is the product of the area and the what axis is there. Okay, from the axis. Then what is the x bar and y bar? This is the distance is given from the centroid to the base. Okay, means if you have taken the rectangular section, then what is the y bar or x bar of that? D by 2. Because you have to change the total depth of that given section. D is there. You have to take this distance is a y bar and this distance is a x bar is there. Is this distance how much you will get? D by 2 is there. D by 2 is there. Okay. Clear? What is the bending stresses or flexural stresses? The stresses is induced in the beam to resist the bending moment. It is known as a bending stresses, and it is denoted by the sigma or M. And sigma is equal to, we can write M by Z. Again, what is the M? Moment of resistance. And what is the Z? Z is the sectional modulus. It is the ratio of moment of inertia to the centroid distance from its neutral axis. From its neutral axis. Check that. Here is the neutral axis at the center. From the any base or top, you will get the distance, half distance. Okay, this is called as a y bar or x bar. You can easily calculate that two value. Okay, I will be getting. Then next bit is a simple bending or pure bending. What is meant by simple bending, or what it is also called as a pure bending. Simple bending, or we can say the pure bending. Okay, I will explain this. What is the simple bending or pure bending with the help of one example. Okay, I will consider here one simply supported beam. Okay, having the load W at a distance A from each support. Okay, this distance is given support. A distance is given from each support. I will write here A, B, C and D is there. Okay, this distance is given. With the help of that example, you can remember the definition of the simple bending or pure bending. Okay, here I have considered one simply supported beam having the load W. Okay, from at a distance A from each support. Okay, if you have drawn the shear force diagram for that SFD, and how to do this diagram, you will get. See, I will draw this. There is support reaction at A point. Then B are in downward direction. Then this one will get this. Okay, this is the W. Again here is the W minus plus. This again A, B, C and D. We have seen in the second unit. Right. Again, if you have drawn the PFD diagram for this loading diagram, then check that. I will draw this BMD. Say you will get this. And what is the moment at point? This is the W wave, and this one 0. A, here is B, and here is the C and B is there. This is the BMD. Okay. Then what is meant by simple bending or pure bending? Okay. When the beam is subjected to the constant bending moment, when the beam is subjected to the constant bending moment, this value will not change in the bending moment, and the shear force is 0, or we can say the shear stress is 0. Check that in the SFD. In between B and C, there is a shear force is a 0. In that portion of the beam is called as a bending, simple bending or pure bending. All of you getting what is meant by simple bending or pure bending? You can pop that example. You can remember the definition. When the beam is loaded, then see in the bending moment diagram, you will get the constant bending. Constant bending. Okay. That constant bending. What about the shear force or shear stress? Shear force is 0. Shear force is 0. Okay. In that portion of the beam is called as a pure bending or simple bending. In this unit, you have to consider only the simple bending or pure bending. Okay. Here you get the numerical amount in the simple bending or pure bending. That's why you should remember the what is meant by simple bending or pure bending. All of you clear? Yes. When the beam is subjected to the constant bending and shear force is 0, at that portion of the beam is called as a pure bending or simple bending. And next bit, third bit is the nature of bending stress. Okay, nature of bending stress. Okay, there are two types of the nature of the bending stress. First is a simply supported beam. Yes, first we will see the simply supported beam, and second nature is a cantilever beam. Simply supported beam. The nature of the beam is a simply supported beam. Okay, remember that whenever beam is loaded, then this beam will be bent. Okay, here again we will consider the simply supported beam. Okay, we will consider the simply supported beam. Okay, A point and B point in the support layer, and here is a neutral axis of that beam. If you have taken the cross section of that beam, then you will get the rectangular cross section, right? This is the cross section of the beam. And check that here I have not showing any load on that simply supported beam. Then you will get the actual cross section of this beam is not bent. If you are acting the some load on the given beam, then this beam will be bent. This beam will be bent. How to bend? See, in this way, if you have taken the section, okay, then take that, we will draw here, that beam will be bent in this way. I will take the section of that, in between that. In this way, this beam will be bent. Okay, here is a point, here is a B point. For equilibrium, we have seen in the first unit, say which stresses are induced above the neutral axis and which stresses are induced below the neutral axis. Check that. Here is a, you will get here, see, there is in the simply supported beam, here you will get the compressive stresses. You will be compressed, and here also you will get the compression. And below the neutral axis, you will get the tension. I will show you the cross section. Again, check that. Here you will get the which type of the stresses, compression stresses above the neutral axis tension is there. And also you can calculate the depth from the top, you will get the YC, and at the bottom you will get the YP. What is the YC? The distance between what we can say the top and centroid, or from the neutral axis. And YP is the distance from the bottom to the up to the neutral axis. You will get the tension. Okay. Then how to draw the bending stress diagram? Okay. Maximum time you will ask the draw the bending stress diagram. Okay. How to draw this? Maximum to minimum. Maximum to minimum. Here you get the stresses induced in the given beam for the simply supported beam. Here above the neutral axis is sigma c, compressive stresses, and these stresses will be reduced, okay, from the top fiber to bottom fiber. Here you will get the 0. At the neutral axis there is a no stress is induced. Remember that. This is our option. No stress is induced. Then again you will get here at the bottom. Here you will get the sigma T. Okay, tensile stresses are induced. This is the bending stress diagram. Maximum numerical you have to ask draw the bending stress diagram. Bending stress diagram. Okay, all of you clear? Yes, for the simply supported beam, above the, you have to remember only above the neutral axis there is a compression stress are induced, and below the neutral axis there is a tensile stresses are induced. And you have to remember this diagram also, bending stress distribution diagram. Okay, maximum fiber to they are travel to the minimum. Again you will get the 0 at the center because there is a no stresses are induced. That's why you will get the 0 stress at the neutral axis. Then after that again slowly this stress is induced. You will get that at the bottom fiber. Again maximum stress are induced. Okay, means sigma T is there. Similar way for the cantilever beam. See what happened in the cantilever beam. If you have taken whenever this cantilever beam is loaded, just that I will draw here again cantilever beam, cantilever rotated beam. Okay, we are acting any load on the cantilever beam, then see what happened. Again I will draw here. If the load is not acting on the cantilever beam, then you will get the cross section, that cantilever beam again rectangular cross section. If the load P is acting at the free end, then how to bend this? How to bend this in this way? This will be bent. Check that. I will take the in this way. This will be bent, right? In this way, this beam will be cantilever beam will be bent. Then which stresses are induced above the neutral axis and below the neutral axis? Check that. Above the neutral axis here, which stresses are induced? Tensile stresses are induced. Tensile stresses are induced. In opposite to the, we can say that to the with simply supported beam. Means if you have shown the cross section of that beam, then check that here above the neutral axis we will get the tension, and below the neutral axis we will get the compression. Okay. Then check that how to draw the bending stress distribution diagram. Here you will get the tension. Okay, sigma T from maximum to the minimum. You will get the bottom sigma C is there. This is the bending stress distribution diagram. Means vice versa. If we have seen the simply supported beam here above the neutral axis, we will get the compression. But in the cantilever beam, we get the tension, and below the neutral axis, we will get the compression. Then this one is the YT. The distance from the top to the neutral axis, and YC is the distance from the bottom to the neutral axis, so IC is the distance. At the neutral axis you will get the zero bending stress, zero bending stress. Okay, I want you getting that three things. You have to remember that. Okay, then today we'll stop here. Next lecture again we'll see the different assumptions. Okay, thank you.